Hi, my name is Sam Lee, and today I'm presenting Lab 5, Free Fall of Slinky. The goal of this lab for me was to first analyze the motion of the bottom of a falling Slinky to see whether it moved at all or how it moved. The lab procedure was to first use Tracker to analyze the motion of the bottom of the Slinky and create an experimental model for that Slinky, to then create a computational model of its motion using GlowScript and physics principles, and then to compare both experimental and computational models. The physics principles used in this lab are the gravitational force Fg equals mg times y hat, Newton's second law, which just states that change in momentum over change in time equals F net, and the tension force, which in this case is opposing Fg. And we'll get to that at the end of the lab. So the first thing I did in Tracker was was use the man's height as reference. We weren't given the man's height, so I assumed an average height of about 1.800 meters and set the origin to the bottom of the Slinky. And after I plotted all the points, this is the graph we got. As you can see, it's mostly close to flat throughout about 5.7 seconds in. And then after that, it goes straight down in almost a straight line. So for GlowScript, the first thing I did was edit our constants. So for the mass, I used 0.200 kilograms because that's the average mass of a Slinky, of a metal Slinky. I used the initial position of 1.8 meters that I used in Tracker. I used t equals 0 because that's where the time started, and then delta equals 0.01, which is the size of each time step. I used g equals 9.8 to represent the acceleration due to gravity. And then for j hat, I used the vector 0, 1, 0, and that was just to give the direction of the motion of the Slinky. I then replaced the physics principles in this lab, so under the while loop, I changed the time to about how long the Slinky was in the air, so it was about 8.21 seconds. And then I found net force, which I just said W, which is the force due to gravity, is equal to negative ball dot m times g, the gravitational acceleration, times j hat. And then I got the magnitude of V, which is mag times ball dot velocity. And then I used this information to apply the momentum principle. And then I use ball dot velocity equals ball dot velocity plus F net slash ball dot m times delta ball dot position equals ball dot position plus ball dot vel times delta. This is just Newton's second law. Change in momentum over change in time equals F net. And so for experimental versus computational models, as you can see, they're extremely similar. They both stay really close up until this point right here, and then they go down in a close to straight line. So the experimental one is blue. As you can see, it's kind of jagged because there were many frames in the video, and so it was hard to get a very straight line for all the points, and there was some human error in placing points. Okay, so what is happening here? As you can see, the bottom of the Slinky doesn't move for most of the time the Slinky's in the air. And the reason for this is because when the man dropped the Slinky, or before he dropped it, but when he let the Slinky extend, when it reached the bottom, it was in its equilibrium position, which means that all the forces are balanced out. And in this case, the forces being balanced out are Fg and the tension force Ft. And so what happens here is Ft balances Fg all the way while the Slinky is extended until the Slinky is fully compressed, and then after that, there's no more tension force, so the Slinky just falls with acceleration due to gravity. And as you can see from the previous graphs, it falls at a very steep line. There wasn't much time for the Slinky to accelerate, so the graph line seems straight, but if the Slinky were dropped from higher, you would be able to see that it curved out exponentially because of acceleration.